Hello students, we are dealing with unit 2 inverse Laplace transform, and in this unit till now we have seen three different methods to find inverse Laplace transform of the given function f bar of s. Now we will move to the next method, that is use of differentiation of phi of s, or we can say that use of differentiation of f bar of s. This method is very simple method, and the examples where we are going to use this method are very particular examples. So it is very easy to identify the examples where we are going to use this method. You will know this after solving the examples. Now first we will see the procedure to apply this method. By multiplication by t property of Laplace transform, we have L of f of t is f bar of s, then L of t f of t is equal to minus d by ds of f bar of s. This property we have seen in unit 1 Laplace transform. Now we are going to use this property here to know how to apply this method. Now if there is a function f of t and it is multiplied by minus 1 by t, if its Laplace transform is f bar of s, then applying multiplication by t property to this function, we get this term, that is L of t into minus 1 by t f of t, and RHS becomes minus d by ds of the original f bar of s. But here t and minus 1 by t get cancelled, so we get the next step. So it becomes L of minus f of t minus d by ds f bar of s as RHS. Now by linearity property on LHS, we can write this as minus L of f of t is equal to minus d by ds of f bar of s. So minus sign on both the sides get cancelled, and we get L of f of t is equal to d by ds of f bar of s. Taking inverse Laplace transform on both the sides of this latest result, we get f of t is equal to L inverse of d by ds of f bar of s. This f bar of s is from this one, whose original function of t is minus 1 by t into f of t. Out of this we have got minus 1 by we have got only f of t. So we get L inverse of d by ds of f bar of s is equal to f of t, then L inverse of f bar of s, this original one, is minus 1 by t f of t. That is, if inverse Laplace transform of derivative of f bar of s is f of t, this f of t is one of the part of the required function of t. So just by multiplying this f of t by minus 1 by t, we get the required answer, that is we get L inverse of the given f bar of s. So for this reason we require to apply the differentiation formulae so that we will get the answer very easily. So here in these examples, first step is simplify the function f bar of s. Second step, take its derivative, find inversality of that derivative using the previously studied methods, that is use of standard results, use of shifting theorem, or method of partial fraction, and then whatever f of t you will get at this step, just multiply that term by minus 1 by t, so you will get the final required answer. You will get this idea very clear through the examples. The question will be as it is: find the inverse Laplace transform of. First example, log of s plus a upon s plus b. So this is our f bar of s. We will consider it as f bar of s. But before taking its derivative, we will apply the laws of logarithm to simplify the function so that we will get the derivative in simple form. So we know that log of m upon n is equal to log m minus log n. So this becomes log of s plus a, that is log of numerator, minus log of denominator. Here it is log of s plus b. Now we have to differentiate this function of s on both the sides with respect to s. So we get d by ds of f bar of s is equal to 1 upon s plus a minus 1 upon s plus b. Why this is so? Because derivative of log function is 1 upon function into f dash of x. Here the function is simple one, that is s plus a and s plus b. So derivative is only 1 upon s plus a minus 1 upon s plus b. So here this is the first step to simplify the given function if possible, then to take the derivative of f bar of s. Now the third step is to find inverse Laplace transform of this latest derivative of f bar of s result. Now as we know that 1 upon s plus a and 1 upon s plus b, these are similar to the standard result 1 upon s plus a. So we can find their inverse LT very easily as e raised to minus at and e raised to minus bt. So here we have got L inverse of d by ds of f bar of s as e raised to minus at minus e raised to minus bt, which is our f of t. So this is the third step. First step is simplify the function. Second step is find the derivative of that simplified f bar of s. Then apply inverse LT results and find f of t. Now the last step is we have to just multiply this f of t by minus 1 by t so that we will get the required inverse Laplace transform of the given f bar of s. So here we have to write the result which we are going to apply. That is, if L inverse of d by ds of f bar of s is f of t, then L inverse of f bar of s is minus 1 by t f of t. Now, so required result is L inverse of f bar of s, that is this function L inverse of log of s plus a upon s plus b is minus 1 by t into this obtained f of t, that is here e raised to minus at minus e raised to minus bt. You can simplify this further so that it becomes 1 by t into bracket e raised to minus bt minus e raised to minus at, multiplying this by this minus 1 to these two terms, we get 1 by t into bracket e raised to minus bt minus e raised to minus at. Now the second example, 1 upon s log of s plus 3 upon s plus 2. Here we are going to take f bar of s as only log of s plus 3 upon s plus 2 and not this 1 upon s. You might be remembering that when we find Laplace transform of integral, whatever the Laplace transform of integrand we have obtained, we just multiply that result by 1 by s. So surely this 1 by s from this given function is indicating that there is integration from 0 to t in the required f of t. We will see it at the end of this solution. Now first step we have done here, simplify the function using laws of logarithm. Again same as in example 1 we have done here, log of numerator minus log of denominator. Then the second step, that is to find the derivative of this f bar of s. Again very simple function, log x, that is 1 upon x is the derivative. So it becomes 1 upon s plus 3 minus 1 upon s plus 2. Third step, take inverse LT on both the sides using the previously studied methods. Here again it is very simple, similar to 1 upon s plus a result, whose inverse LT is e raised to at. So here we are getting f of t as e raised to minus 3t minus e raised to minus 2t. Now only one step is over there. So L inverse d by ds of f bar of s is equal to f of t. Then L inverse f bar of s is minus 1 by t f of t. Now using this result we get L inverse of log of s plus 3 upon s plus 2, that is L inverse of f bar of s, this f bar of s, as e raised to minus 2t minus e raised to minus 3t by t. Now we will find L inverse of this complete term, which is having 1 upon s. Just now I have told you that because of this 1 upon s, it is sure that there should be integral sign in the required f of t. So we have to just take integration from 0 to t of this latest f of t, that is L inverse of f bar of s. Now here we can write this with notation u. Just replace t by u in the integrand. So we get integration from 0 to t e raised to minus 2u minus e raised to minus 3u whole divided by u and integration with respect to u. So this is our required answer. Next example, log of s square plus 1 upon s into s plus 1. Again the same procedure as discussed in the first example. Consider f bar of s as the given function. Apply laws of logarithm. Now observe here, the denominator contains the product of two terms, but these two terms are in the denominator, so while writing it with log sign separately, we are taking it with negative log, that is minus log. So log of numerator minus log of denominator, log of s square plus 1 minus log of s minus log of s plus 1. This is the first step. Now we will find its derivative. Log of f of x derivative formula we are going to use here. So it is 2s upon s square plus 1 minus 1 upon s minus 1 upon s plus 1. Taking inverse LT on both the sides, we get now L inverse of 2s upon s square plus 1. By linearity property of inverse LT, it can be written as 2 L inverse of s upon s square plus 1 minus L inverse of 1 upon s and minus L inverse of 1 upon s plus 1. Now using the method of standard results, we can find these answers as 2 cos t minus 1 minus e raised to minus t. So this is L inverse of d by ds of f bar of s. Now the final step is to just multiply this latest result by minus 1 by t. So first we have written here the standard result, then multiplying this term, this f of t, by minus 1 by t and simplifying, we get this final required answer 1 plus e raised to minus t minus 2 cos t whole divided by t as a final answer, which is inverse LT of this given f bar of s. Next example. Now here the f bar of s is containing tan inverse functions. In unit 1 we have seen that we obtain the results as tan inverse or cot inverse of some functions of s, where we are taking the division by t property, as division by t property is involving integration from s to infinity of f bar of s ds. Okay, now we will see the procedure. Consider the given function as f bar of s. Then here, as it is containing tan inverse, so it is similar to tan inverse f of x, What is the derivative of tan inverse f of x? It is nothing but 1 upon 1 plus f of x square into d by dx of f of x. Here f of x is written as 2 by s. So it becomes 1 upon 1 plus 2 by s square into derivative of 2 by s. Simplifying this function, we get d by ds of f bar of s as 2 upon s square plus 4. Now the next step is to take the inverse LT on both the sides. Then by applying linearity property and using L inverse of this function using the standard result method, we get f of t over here as minus sine 2t. Now L inverse of f of s is f bar of s is minus 1 by t into minus sine 2t, that is sine 2t by t. Next, cot inverse. Again the same procedure as in case of tan inverse. The derivative of cot inverse x is minus 1 upon 1 plus x square. Here instead of x, s plus 1 function is there. So first step, directly take the derivative of the given f bar of s, minus 1 upon s plus 1 square plus 1, taking inverse LT on both the sides. Now here minus 1 is there, so by linearity property of inverse LT, we can write this minus 1 outside the L inverse operator. Now using shifting theorem of inverse LT. Why to use shifting theorem? Because here s is not present, but it is with some linear term plus or minus 1. So s plus 1 indicates that we have to use here shifting theorem of inverse LT. So applying that method, we get e raised to minus t L inverse of 1 upon s square plus 1, and this minus 1 multiplier is as it is over there. L inverse of 1 upon s square plus 1 is sin t. So f of t is minus e raised to minus t sin t. And the final step, just multiply this function by minus 1 by t, so that you will get the answer as e raised to minus t sin t by t as the final answer. So these are the unique examples where we have applied this method. Now you might have observed that this method can be applied only to the functions f bar of s which are having logarithmic functions, inverse trigonometric and inverse tan and inverse cot functions. So we can easily identify the examples where we can apply this method. The steps are very simple. First, simplify the function if it is involving logarithmic function. Then second step, take the derivative of f bar of s. Third step, find L inverse of this derivative. And then fourth step, multiply the obtained f of t by minus 1 by t. So this method is very simple. In 50% of the university question papers, there are such type of examples asked. So this is very simple and scoring method. Here I have given some examples for practice. The question will be same. First example containing log term. Answers are also given. Second function containing tan inverse. It is similar to the fourth example which already we have solved. And third one is cot inverse. It is similar to the fifth example. So here answers are given. You may verify the answers you have obtained using this method with these given answers. Thank you.